In this next step, we'll be making decisions about recording data in ways that will help us answer our questions. This process is also known as data management.
Data management involves making decisions about data. The codebook and frequency distributions are an excellent guide for making these decisions. In fact, many decisions that you make will be based on examining frequency distributions. You will use them often because they reveal things about the data that will be helpful to you.
There are several steps commonly considered when conducting your data management. You may only need to perform a subset of these steps. It is even possible that your variables are already adequately managed and no data management is necessary. In all cases, it is important that you consider each possible decision because it allows you to play an active role in understanding your data and assuring that you are asking your questions in an appropriate and meaningful way.
A first step to consider is whether or not you need to code out missing data. We'll use our young adult smoking project as an example. In the NISARC codebook, you see that the response category 1 means daily smoking for variable S3A Q3B1. And you can read down to see the meaning of other response categories for the usual smoking frequency variable and frequency table. Your data will often include response categories that don't help you answer your questions, even though they provide information. For instance, in this variable, we have a response category unknown coded as a 9. For these responses, we simply don't know how much these individuals smoked, and therefore we don't want to include them in our analysis. We want to set this response to missing to ensure that Stata disregards these values. In Stata, we can do data management to make changes directly to this variable, S3A Q3B1. However, it's often good practice to first make a copy of the variable we want to data manage, and then make changes to that variable copy. This way, the original variable values will always be in our data set, and so if we make any errors in data managing our variable copy, we can easily just delete that and go back to our original variable again. As an added bonus, we can also name this variable copy something more intuitive. So let's first start by making a copy of a variable. To do this, let's write the code gen freak smoke equal S3A Q3B1. The command gen is short for generate, and it tells Stata to generate a new variable that's an exact copy of S3A Q3B1. That is to say, if an individual reported a 3 in this variable, she or he would also have the value 3 in the new variable we just added to our data set called freak smoke. Now, moving forward, we can make any data management changes to freak smoke that we want. As we just noted, the value 9 in this variable should be recoded to missing. The code that we add to our program to accomplish this is replace freak smoke equal period or dot if freak smoke equal 9. We're telling Stata that any observation in this variable that is currently a 9 should be recoded as a period or dot. A dot is the way that missing data is specified in Stata. Notice that in the first half of our line, we use only one equal sign, whereas in the second, we use two equal signs. It's important to remember that in Stata, two equal signs tell Stata that something is currently equal to, whereas one equal sign essentially means set as equal to. So our command reads as set freak smoke to be equal to dot or missing whenever freak smoke is currently equal to 9. Here's another look at the Stata program we've been building for this example project. When we execute our generate and replace codes, the results window shows how many changes were made and what those changes are after the replace command. To further check that this logic statement accomplishes what we intended, let's also run a frequency table. Tab 1 freak smoke. As you can see from this new frequency table, the 3 cases that were set to 9 are now missing and not visible in our frequency table. So this variable has been managed. If you'd like to further confirm that these observations are in fact missing, you can add the optional argument MIS to your tab 1 command. Tab 1 freak smoke, MIS. If you execute this command now, the frequency table will include a row for the number of missing observations. This is also helpful in confirming our data management is successful. Let's consider another of the variables in the sample project, S3A-Q3C1, the variable usual smoking quantity. Here's the codebook entry for this variable also. Usual number of cigarettes is indicated by values of 1 to 98. A value of 99 indicates an unknown response. It's this value that we need to set to missing, since it doesn't measure the number of cigarettes smoked, but rather indicates that we have no information on cigarette use for individuals who are coded as a 99. To do this, we need to use the generate replace set of commands again. Gen quant smoke equal S3A Q3C1. Replace quant smoke equal dot if quant smoke equal 99. We add these commands to our program, then also add a command to run a frequency table, save our file, and then execute these commands. As always, check the results window to see if there are any error messages, and then look at the results. When we look at the results window to examine the new frequency table for usual smoking quantity, we can see that the 9 observations that were originally set at 99 are now in the missing group. What's next in data management? When we examine the frequency distribution and the codebook entry for the tobacco dependence variable for our sample project, we see that this variable has only valid responses. That is, 1 equals nicotine dependence, and 0 equals no nicotine dependence. So this variable will not require any data management for missing this, and we're set to move forward.
Please note that it is important that you examine each of the variables that you've selected and add syntax to your program that recodes appropriate data as missing. Once you have completed this portion of the data management, the next step is deciding whether or not you need to code in valid data that has been unnecessarily set to missing.
In some data sets, particularly those based on surveys, there are often skip patterns. So you may ask participants in a survey, have you ever been arrested? And a respondent may say no. If the next question in the survey is how many times have you been arrested, for a participant who already reported never having been arrested, this second question just doesn't make sense. To avoid asking inappropriate questions, skip patterns are often created in surveys that allow participants to skip questions in which the answer can be logically determined. In this way, missing data on some questions might mean that we can reasonably recover valid information.
For the question, did you drink at least one alcoholic drink in the past 12 months, 16,116 participants said no. These individuals would not need to be asked the question about how often they drank alcohol in the past 12 months.
Instead, they will be set to blank, or in the case of Stata datasets, a dot or period. So for the variable, how often did you drink alcohol in the past 12 months, it would be reasonable to code this as valid data rather than missing. To recover this valid information in our program, we would use these generate and replace commands. Gen freak drink equal S2A Q8A. Replace freak drink equal dot if freak drink equal 99. Replace freak drink equal 11 if freak drink equal dot and S2A Q3 equal 2. In other words, if how often drank any alcohol in last 12 months is blank, that is shown as a dot in a Stata dataset, then we know that the individual drank 0 times in the last 12 months, and we can give them a valid code. However, we're adding if S2AQ3 equal 2 to our logic statement in order to include those observations who answered no to this variable, since our category 11 includes all non-drinkers. This way, rather than left as missing, we're adding a category to this variable with a dummy code of 11 to indicate those participants that we know from another variable did not drink alcohol in the past 12 months.
Another very useful step in data management is to give your variables response codes that may be more logical than those they were originally given. For my variable, usual smoking frequency, you can see from the codebook entry that lower values mean that the respondents smoked more, and higher values means the respondents smoked less. Perhaps this seems counterintuitive to you.
We could choose to reverse code this variable so that higher values mean more smoking and lower values mean less smoking by adding the following code. This syntax creates a new variable called USFreak that reverse codes each of the smoking levels. Now, smoking every day is a 6, and smoking once a month or less is a 1, and all intervening levels have been appropriately reversed also. Rather than using the original variable S3A-Q3B1 in our analysis, we will use this new variable USFreak. As always, it's important to add these details to the codebook and to comments in the program so there's good documentation of this decision as we move forward. But there's actually another option that may be even better for giving this variable codes that are maximally appropriate. In a way, dummy codes 1 through 6 are unnecessarily categorical, given that how often you smoke is generally a quantitative variable. And it may be reasonable to recode the variable in order to capture more of its quantitative features. To do this, we choose values that reasonably correspond to the number of times each individual smokes in a usual month. So someone who reports smoking every day could be said to smoke cigarettes on 30 days in a usual month. Someone who smokes 5 to 6 days a week could be said to smoke 22 days in a usual month. Someone who smokes 3 to 4 days a week could be said to smoke 14 days in a usual month. Those smoking 1 to 2 days a week would be 5 days in a usual month. 2 to 3 days a month would be 2.5 days in a usual month. And once a month or less would be 1. Although these are estimates, they capture the quantitative nature of the measure and also keep individuals ordered in terms of the frequency with which they smoke. Note that the way we've written the syntax, our new variable is called USFreakMO, which stands for number of days smoked in a usual month. So this even makes more sense, doesn't it? What we've basically done is to spread the measurement of smoking frequency out in a meaningful way, so that while it's a categorical variable, we're actually getting more information out of it than we had originally been given. When we request a frequency table for the new variable USFreakMO, including missing or unknown data, the table now describes the sample of 1,706 young adult past year smokers somewhat more clearly by showing the numbers and percentages of individuals who smoked these approximate number of days in a usual month. You can see that the vast majority of the sample, 1,320 individuals, or 77.37%, smoked 30 days a month. Fewer than 5% smoked 1 or few cigarettes a month. One of the later steps in data management is evaluating whether you might want to create secondary variables. Secondary variables are variables that include information from 2 or more primary variables. We can create secondary variables by using a mathematical or logical operation on 2 or more variables. In this case, we want to know the number of cigarettes smoked per month. We know the number of days smoked each month, and our new variable, USFreakMO, gives us an estimate of the quantity smoked. If we want to estimate the total number of cigarettes that participants smoked per month, it would make sense to multiply these two variables, USFreakMO and QuantSmoke, and get a product that represents the number of cigarettes per day times the number of days smoked per month. Let's call this new variable numsigmo_est, which stands for the estimate of the number of cigarettes smoked per month. So the syntax would be generate, or gen for short, numsigmo_est equal US freak mo asterisk quant smoke. If we add this line of code to the program and ask Stata to show us the frequency distribution for this new variable numsigmo_est, we can see that it is a quantitative variable that ranges from 1 to 2,940 with 9 missing observations. So how can we check to see that this new variable was created as we intended? Perhaps the quickest way to do this is to browse our data again, looking at our relevant variables to get a sense visually of whether the original variables were recoded into the new variable the way we want. We've already used point and click to browse our data by clicking on the icon that looks like a magnifying glass over a spreadsheet. We can also do this using the command browse. Even better, when we use this command, we can add specific variables after it, and Stata will then only show the requested variables in the browse window. So we're going to add the following syntax: browse, followed by a list of variables that you'd like to examine for each observation or individual. Since we want to see if the new variable, number of cigarettes smoked per month, is indeed the product of multiplying frequency per month and number of cigarettes per day, we include the following variables: US freak mo, quant smoke, and the new secondary variable numsigmo_est. After saving the program and executing the command, the browse window will appear. Just as we saw before, the rows represent individual observations, and the columns show the values for the specific variables. Looking over these values for a handful of variables, we can see that, in fact, our new secondary variable does indeed show the value of number of days smoked per month times number of cigarettes smoked per day. Remember that whenever you're conducting data management, it's important to find a way to check for errors at each step of the process.
So what if you want to combine more than two variables? A good example of this would be creating a single secondary variable to characterize ethnicity from a number of separate primary variables available in the AddHealth data.
In AddHealth, race or ethnicity are measured by a series of questions, coded 1 if yes and 0 if no. Since adolescents in this sample could have indicated more than one race or ethnicity, we could decide to characterize those adolescents who indicate multiple racial or ethnic groups separately from those who could be characterized with a single ethnicity. To accomplish this, the first thing to do is sum the variables to get a new variable, which we'll call numethnic. That indicates the number of race or ethnicity variables that were endorsed. The syntax would include the new variable's name equal to sum, open parens, of, and then each of the variables listed with only a space between them, followed by a closed parens and a semicolon. Here we have a new do file setting the directory to AddHealth using the AddHealth database and sorting the data according to the unique identifier for this database. To accomplish the task of characterizing adolescents who indicated multiple ethnic groups separately from those indicating a single ethnicity, the first thing to do is to make copies of the original variables and then data manage the variable copies to remove the 6s and 8s, which indicate the participant refused to answer or did not know about their ethnicity. Then we will sum the variables to create a new variable, which we'll call numethnic, that indicates the number of race or ethnicity variables that were endorsed. The syntax would include the generate command just as before, but then after the equal sign, we say white plus Asian, etc., for all the ethnicity variables we've identified. Gen numethnic equal white plus Asian plus Amend plus AFAM plus HISP. Please note that the variables are not capitalized in the AddHealth dataset, and we must match the case exactly for variables in Stata code. Note that this will only generate a sum if none of the observations in a given row have missing data. If at least one observation in a row is missing, this new variable value will be missing as well, because Stata does not know what the final sum would be and does not want to misrepresent the data. Once we've done this, we can then add code to create a single secondary variable that characterizes each adolescent's ethnicity. First, we generate our final ethnicity variable, which we'll call ethnicity, and set it equal to missing. Instead of starting with a variable being an exact copy of another variable, then coding out certain information, we're going to start with every row in this new variable being missing, then code in certain information. For example, we'll indicate that multiple ethnicities were endorsed with replace ethnicity equal 1 if num ethnic greater than or equal to 2. Ethnicity equals 2, which means only Hispanic or Latino ethnicity was endorsed, if H1GI4 equal 1 and num ethnic equal 1. Ethnicity equals 3, only Black or African American ethnicity was endorsed, if H1GI6B equal 1 and num ethnic equal 1. Ethnicity equals 4, only American Indian or Native American, if H1GI6C equal 1 and num ethnic equal 1. Ethnicity equals 5, Asian or Pacific Islander, only if H1GI6D equals 1 and num ethnic equal 1. Ethnicity equals 6 for white ethnicity only, if H1GI6A equal 1 and num ethnic equal 1. When we add the syntax for data management of ethnicity, also request frequency tables for the old and new ethnicity variables, hit save, and then execute the command. Here's what we get. We have our output, which shows the frequency distributions of all the original variables and the primary and secondary ethnicity variables. This program is available as text below this screen. We suggest you copy this text and paste it into a Stata program window and select Run. Examine the output and consider how this kind of data management might be useful in answering your question with your dataset. This example should help you make the needed connection between data management decisions and syntax. Once you've created the secondary variables that you feel you will need, you can also consider whether any of your quantitative variables or categorical variables need to be further grouped or binned. As an example, we're going to show you how we might choose to group age in the NESARC sample. If, rather than looking at age as a quantitative variable, we may want to compare age groups categorically. We could examine the number of observations at each age and make some decisions about how we could best make groups. Here's the frequency table for age in our young adult past year smoking sample. Tab 1, Age. The cumulative percent column displays percentiles that can help you divide the sample into a specific number of equal parts. If we wanted 4 age groups, we would look for cumulative percentages that are closest to 25%, 50%, and 75%. If we wanted 3 age groups, we would look for cumulative percentages that are closest to 33% of the sample and 66% of the sample. This is the syntax that would create a categorical variable that divides the sample into roughly 3 equal-size age groups. We chose the age cut points of 20 and 22 because these correspond roughly to the 33rd and 66th percentile. Gen age group equal dot. Replace age group equal 1 if age is less than or equal to 20. Replace age group equal 2 if age less than or equal to 22 and age is greater than 20. Replace age group equal 3 if age is greater than 22. The frequency distribution table for our new variable age group shows the 3 age groups and the percentage of observations in each group.
Now that you've seen a number of different data management decisions that could be made, I hope that you're ready to take on your own, which you will do in the next assignment. How much data management you will need for your own variables will depend on the variables that you've selected and the decisions you've made about them. Some may choose to only code out missing data, while others may need to or want to do more. Data management is a part of the research process that you can and will return to again and again as you learn more and are able to make better decisions.